So let's move forward with this geostrophic flow that we had in the XYZ coordinate, and we simplified that for the compressible incompressible fluid as non-divergent in the horizontal, and W0 for a flow that starts at a surface with the W0, dW dz was 0, using our non-divergence of the incompressible fluid mass continuity equation. Okay, so here is our geostrophic velocity vector in the pressure coordinate. Looks very similar, except that we have replaced the pressure gradient with the height gradients on constant pressure lines. Okay, so we are in the pressure coordinate. We have dropped the constant P here from the previous equation. So look exactly the same, but note that instead of dp dy we have dz dy and dz dx. Obviously we can take dug dx dvg dy and we get dz dx dy dz dx dy with minus and plus signs, which means we are going to end up with grad p dot ug pressure coordinate equals du dx plus dv dy equals 0. Looks exactly the same as the incompressible fluid. Okay, so you remember your fundamental fluid dynamics that when you have a non-divergent flow, you can define a stream function, a general form, which is x, y, p, and t, where p is the pressure coordinate we are using. So in that case, you can define the geostrophic currents as the gradients of the stream function, obviously minus d psi g dy, and vg is d psi g dx, right? That looks just like dz dy and dz dx, because height contours on a pressure surface are stream functions of geostrophic flow. Okay, when you have a z coordinate, you draw z lines and you have z surfaces. When you have pressure coordinate, you can take pressure surfaces. A pressure surface varies in height, but you can draw height contours on the pressure surface, right? So that's what this is saying, that height contours on a pressure surface are streamlines of geostrophic flow. So their gradients are geostrophic flow. Ug is minus d psi g. So here the stream function is just g over f times z. Okay, z is the height of the pressure surface. Okay, looks very confusing, but go through it again, make sure you understand it. So again, height contours on a pressure surface are contours of geostrophic flow. You can see that here. Now going back to our 500 millibar geopotential height, we put winds on top, and you can see that these are height contours of the 500 millibar, right? So we said we are going from let's see, where are we? The map. So here we are in California. So we are going from low latitudes, tropics here, so Gulf of Mexico, and so on. So we had 5.8 or 9 kilometers here, dropping down to by about several hundred meters as we go towards the poles, because the pressure surfaces dip as we go towards the poles, right? Temperatures get colder, atmospheric column compresses, and the pressure surfaces geopotential height falls. We had seen this before, but now look carefully here. Okay, these are the wind vectors shown as these what are they called? I just forgot. So quiver and the line, right? So these quivers are the scale. So the wind flows away from the quivers. So each quiver here, the length is 5 meters per second. So if you have 2 quivers like this, it means it's 10 meters per second and it's pointing in this direction. Okay? So basically you see geostrophic flow, and you can see some acceleration here, as we said before. As the height contours compress, the geostrophic flow accelerates. You can see this more than 10 here, 10 plus maybe 12 meters per second, whereas 10 meters per second here. Remember, we had shown how the channel compressed when the pressure surfaces came together. On the constant pressure surface or geopotential height, basically height contours are going to come together and the flow is going to accelerate. So what is amazing? Amazing is that the flows are parallel to the height contours. Okay, which means height contours are streamlines of the geostrophic flow. Obviously, when you go to low pressure centers like this, the geostrophic balance begins to break down. So you can see some flow crossing these Z contours, geopotential height contours, right? We will see that this also means that the Rossby number is not small anymore when you get into these cyclones and anticyclones. Okay, so as long as Rossby number is small and these pressure contours are smooth like this without convergence or divergence, you have flow essentially parallel to the height contours. Here is a high pressure center, and you can see this circulation here, which should be clockwise, so away from the quivers. So this way, this way, this way. So this is a clockwise circulation, whereas here you will have a counterclockwise circulation. Okay, it's fairly straightforward, but get an intuitive sense of what we are talking about. We defined geostrophic stream function, and we went back to our pressure coordinate, and we said height contours on pressure surfaces are streamlines of geostrophic flow, and geostrophic flow is parallel to pressure lines, or in a pressure coordinate they're parallel to height contours. You should be able to switch back and forth. Okay, very simple. So just go through it again and make sure.